Good afternoon, and welcome to Ethanol Producer Magazine's webinar series. I'm Lisa Gibson, editor of Ethanol Producer Magazine, and I'll be your moderator for today's webinar titled Your Roadmap to Total Tank Protection and sponsored by Stover Controls, an Emerson Impact partner. Before we begin, here's a quick word from our sponsor.
Stover Controls has been committed for over 75 years to helping clients run at peak uptime. They make an impact by helping customers address real challenges in their processing plants. By providing a qualified team, customers can depend on Stover to help them run hard, safely, and without unexpected production interruptions. They call that peak uptime. Stover Controls is the local expert in process control automation, which allows them to see what others don't and solve problems others can't because they know their customers like they know their neighbors. As an Emerson Impact partner, Stover Controls belongs to a class of 21 network companies that have completed rigorous certification process of their facilities, procedures, engineers, and local service professionals. They have also demonstrated ability to support customer process optimization and performance improvement programs. Each partner was assessed in more than 50 certification paths to verify capabilities and compliance to Emerson standards. Stover Controls provides local access to global Emerson engineering services and expertise, as well as critical integrated outage services for the full scope of automation and control assets. Representing brands like Delta V Control and Safety Systems and Plant Web Digital Ecosystem Solutions, Stover Controls also supplies and services Fisher, Crosby, Anderson Greenwood, KTM, Keystone, and Vanessa valve and pressure management products to support the entire process lifecycle. From 24/7 emergency response to preventative maintenance or full reliability programs, Stover Controls offers the services you need to keep you running at peak uptime.
A big thank you to Stover Controls for sponsoring today. Don't forget to visit them at booth 209 at the International Fuel Ethanol Workshop and Expo coming up in Indianapolis in June. Before we begin, I have a few logistical items to share. Today's webinar is being recorded and you will be able to find it under the Events tab at ethanolproducer.com. So check for that in the next few days. Also, we'll save questions until the end after all speakers have delivered their presentations, but please feel free to type questions into the designated space on your screen at any time during the webinar. Any questions we don't get to in the allotted time will be forwarded to the speakers so they can follow up after the webinar. And with that, we're ready to get started. We have 4 speakers on our panel today. Paul Wagner, the ethanol industry lead for Stover Controls. Rhonda Bunty, application engineer, pressure management for Stover Controls. Isaac Dressler, sales manager, pressure management for Stover Controls. And Sean Collins-Dipple, process level product manager for Emerson. Our first speaker today is Paul Wagner, ethanol industry lead for Stover Controls. Go ahead when you're ready, Paul.
Thank you. Yes, my name is Paul Wagner, and I am the industry lead for ethanol for Stover Controls. I've been in the biofuels areas for about 20 years now. Emerson and Stover have a long history of providing total tank protection for our customers. We help them ensure safety, achieve product quality, meet environmental regulations, and minimize total cost of ownership by providing proper tank protection, equipment, and services to maintain that equipment. You know, I visit a lot of ethanol plants, and I've seen firsthand how devices that have wires are regularly maintained. Tanks, however, can be out of sight, out of mind. Plants might know what equipment is installed up there, but often don't know how it works and what it's protecting. You may be inspecting your tank safety devices, but do you know what you're looking for? Do you know how to spot an issue? Like pressure management, for instance, it's critical that your tank vents can operate properly when called upon to do so. If they can't perform their function due to excess freezing, sticking, or excess weights like the picture on the top left there, the consequences can be, well, catastrophic. All too often we find these devices are orphaned. They're set up and then not part of any formal maintenance program. Measurement, it needs to be accurate. You need to be confident in each one of your measurements. If they fail, you can overflow your tanks. Some tanks or applications also require special equipment like flame arrestors or tank blanketing equipment. All these devices must work together to meet the operational and safety needs of your tanks and your plant. Today we're going to give you a roadmap for how to address these problems. Today we're going to review the basics of tank protection. It's not possible for us to cover every detail about tanks in this webinar. The next step for you would be attending our full Tank University course or bring in some of Stover's experts on site to do a tank survey. We'll have more information on those at the end of this webinar.
Before we talk about tank top devices, we must first know what type of tanks are out there. There are 3 types of tanks: open top, fixed roof, floating roof. The important difference is as we move from open top to floating roof, we ultimately improve safety and reduce product loss by controlling or trying to eliminate the vapor space in the tank. However, as we move from left to right, the cost of the tank does increase. One of the most common types of tanks is a fixed roof tank. By putting a roof on a tank, we can keep the elements like rain and snow out of the tank, but we must now somehow control the vapor space within the tank. If the products in the tank are non-hazardous, then maybe a simple hole with a rain cover would do. However, in most cases, we want to keep our products from evaporating, and therefore pressure control devices are required. Typically, this is the type of tank we expect to see in fermentation. Some plants, however, do use this type of tank as their product storage tank. Internal floating roof tanks are designed to keep the vapor off of the tank. In order to control the vapor space between the floating roof and the fixed roof, large vents are installed on the top edge, and natural drafts remove any vapors. Typically in the ethanol industry, we see this style of tank used for final storage and storage of flammable products. Today we will focus on fixed roof tanks. Open-top tanks and floating roof tanks don't require as many protection devices. When it comes to sizing, there are a couple of terms that are useful to understand. These are in-breathing and out-breathing. Out-breathing is when the vapor space heats up and expands, or when the liquid is pumped in. This raises the tank's pressure, and the tank needs to breathe out, thus the term out-breathing. We also need to consider the expansion due to the fermentation process. In-breathing is when the vapor space cools down and contracts, or when liquid is pumped out. This lowers the tank pressure, and the tank needs to breathe in, thus the term in-breathing. These are the things that we consider when we're sizing conservation and emergency relief vents, but the calculations are determined by the API standards. There are many different standards for atmospheric or low-pressure storage tanks. API, American Petroleum Institute 620, is most commonly used. This covers the design and the construction of large welded, low-pressure tanks. Temperature ranges -325 degrees Fahrenheit to 250 degrees Fahrenheit and pressure up to 15 psig. API 2000 covers venting atmospheric and low-pressure storage tanks. API 2000 guidelines help to determine how to size pressure relief devices to ensure safety. This is the specification that we use when we size pressure relief devices. The API 2000 7th edition main body is used to calculate the capacity for conservation vents. For fermentation processes, we can assume non-volatile liquid and no tank blanketing regulator, but we do need to consider the CO2 generation from the scrubber failing or shutting down. As you can see, we do require the latitude and to confirm whether the tank is insulated to complete the calculation. Also, standard margins are applied to the pump-in rates depending on whether they are volatile or non-volatile liquids to determine the capacity of the valve. The API 7th edition Annex A is commonly used for emergency relief vents, but it is only valid when the liquid is similar to gasoline. If we were sizing your ethanol storage tank vents, this is what we would use, and it must meet all of the 5 criteria on the left. It must be a storage tank that is uninsulated with a maximum operating temperature of 120 degrees Fahrenheit and with a tank volume of 180,000 barrels or less, and as mentioned, the characteristics should be similar to gasoline. For fermentation tanks, since the liquid is non-volatile, we can still use the main body calculation for emergency relief vents. We can size for both the main body and Annex A in our software, SoftCalc.
Thank you. That was Rhonda Bunty, Application Engineer for Pressure Management at Stover Controls. Our next speaker is Isaac Dressler, Sales Engineer, Pressure Management at Stover Controls. Go ahead when you're ready, Isaac.
All right, we are going to dive into conservation vents and emergency relief vents. So there's a lot of equipment that you can see on top of a tank, and this isn't to say that every single tank in your plant is going to have each one of these devices. We've got emergency vents, conservation vents, tank blanketing, and vapor recovery regulators, as well as any instrumentation that you may need for measurement or level. But what we really want to dive into is how all of these items work together, and we like to think of it as layers of tank pressure control. So our base layer, when we're looking at outbreathing, and like Rhonda said, this is when content's being pumped into the tank, so we have to breathe vapors out. The base layer is going to be our vapor recovery regulator, or common to fermentation, it's going to be a CO2 scrubber, just pulling a vacuum. The next step is vapor to atmosphere, or what we would consider our breathing layer. Then finally, we have emergency venting, which is the last step before we reach a tank rupture. On the inbreathing side, this is when contents are being pumped out and we have to draw vapors back in. We sometimes have a tank blanketing regulator for blanketing gas inbreathing. The next step is oxygen inbreathing from our conservation vent. And then finally, we have emergency inbreathing from our emergency vents before we have a tank implosion or sucking a tank in. So we're going to start looking at the breathing, what we consider the breathing layer, and this is conservation vents. So conservation vents, also sometimes you'll hear people call them breather vents. You'll commonly hear me refer to them today as PVRVs, which stands for pressure vacuum relief valve. We don't like to abbreviate conservation vent to CV because it typically stands for control valve. But there's 2 types of conservation vents out there. You can either vent to atmosphere or pipe away so that you can reclaim the vapors or send them through a scrubber. The nice thing about these devices is they are very simple. Basically how they work is you have a pallet that has a tight seal around the bottom, and on top of that pallet you stack weights to achieve a set point. If tank pressure builds up over that set point, like you see on the top right image there, the pressure will lift the pallet and the vapors are able to escape the tank so the tank can restore to its proper operating pressure. On the flip side, the lower image there, we have vacuum relief as well. Works a little bit different. We still stack weights on the top side to achieve our set point. But what happens is as the tank's pumping out, if we need vacuum relief, when it pulls the vacuum, it'll actually lift that pallet up and allow atmosphere or oxygen to breathe into the tank. There are various different types of conservation vents out there. Most of what we see is going to be a conventional lift. And the main thing to keep in mind when you're looking at conventional lift conservation vents is that they require a certain amount of pressure over set point to get to fully open. We would consider this overpressure or buildup pressure. There's other designs out there that are manufactured so that they go full open at 10% overpressure or less, and we typically call those full lift or pilot operated. So like I said, conventional lift PVRVs are the most common ones that we see across the industry for biorefining and ethanol. just a standard flat pallet, and they open gradually as the tank pressure increases. Full lift is a design that utilizes what's called a huddling chamber, so they go full open at 10% overpressure. However, they do require a blowdown range so that they can reseat. One other advantage to full lift is that they are typically a little bit tighter sealing. They'll leak only up to 1/2 of an SCFH at 90% of set point, whereas conventional lift can leak up to 1 SCFH at 90% of set point. And then finally, we have pilot operated. These devices are more similar to your PSVs throughout your plant. They have tight shutoff at up to 99% of set point. They go full open almost immediately if you use snap acting, or we can have them set up for modulating control. So while you get increased capacity with full lift or pilot operated, as you move left to right here, you also increase the cost of the device as well. So regardless of the style of conservation vent that you use, there's a variety of issues that always seem to affect any users. One of the first ones is freezing or sticking. This is commonly due to poor material choice. And so what can happen is you get moisture or water in there on those days when it's about 28 degrees up here, and it'll freeze the pallet to the seat. Then what can happen is the pallet's unable to lift, and you run the risk of your tank overpressuring or underpressuring and sucking in. It's also common to see this if there's any debris in the vapors that can stick or hang up on the materials themselves, or if they're in near another system that has nasty debris on it. That'll gum everything up, and then they're unable to work. So one way you can deal with the freezing is by insulating them and then either steam or heat tracing them. Obviously, there's additional cost with that. Some manufacturers out there will have special coatings or special materials that you can utilize inside of them. Or eventually, you're just going to have to get to a point where you have an increased maintenance interval and need to take a look at these more frequently. Another common issue that we see is excessive leakage. Damages to the seat where the pallet has to create a tight seal can create a leak path so that you're either getting atmosphere into your tank or allowing your process to leak out. So this can be an issue if you're trying to keep atmosphere out of your product or if you have environmental regulations that you need to keep. Majority of the conservation vents that we see installed have a cast-in seat. And so this means that if you damage that seat in any way, basically what you have to do is remove that from service and machine it down, or take a lapping block out there into the field and machine it until you have a like-new seal. There's also a lot of manufacturers on the market that have designs that allow the pallets to move back and forth as they lift. And then once that happens, they don't always get a proper reseat, and that can create a leak path as well. So these are all things that you need to watch out for and check when you're doing your regular inspections. And then finally, confirmation of the conservation vent actually working. This is similar to any product in your plant. You'd like to know if it's actually working properly. And so one way you can do this is just monitoring the pressure inside the tank. You can set limits for high and low and make sure the tank doesn't exceed those limits. Option 2 would be monitoring the position of your conservation vents, which some manufacturers are able to do. But ideally, we'd be in option 3, which is a combination of the other two, where you're monitoring pressure in the tank as well as the position of your conservation vent, so you know if it's opening at the right time and reseating at the proper time. So Emerson carries a variety of brands for tank protection equipment, but ENARDO is the solution to pretty much all of these problems. You can see there on the left, we can outfit all of our ENARDO products with Rosemount transmitters, so we can feed back to your operating system or to a PLC what the position of the conservation vent is. ENARDO also has a patented Saber Guide system, so that we know that we get nice, clean, repeatable seats every time that pallet lifts, and so we know that we're not getting excessive leakage. And then finally, what I think really sets ENARDO apart from the rest of the market is they utilize PPS as the material for their pallets and their seats. PPS is a proprietary material that has phenomenal chemical compatibility, virtually nothing sticks to it, and also it's rated to -50 degrees. So when we're in the middle of a polar vortex, you can be confident that nothing's going to freeze to that and cause that pallet to be unable to lift. You'll also notice from that cutaway there on the right, the seats are actually removable. So if they ever do become damaged, instead of having to take a lapping block or machine those down, they can be replaced in the field very easily. Now we're going to move to the next layer up, emergency venting. And oftentimes people think of this just as an overpressure protection, but we actually like to use emergency venting to protect on the vacuum side as well. So some common names for emergency relief vents would just be an ERV. Sometimes you'll hear them referred to as an EPV RV, emergency pressure vacuum relief vent. And then finally, there's manufacturers that just call them a blow-off hatch. The two basic styles are a vertical lift design and a hinge design. The vertical lift is just a really simple design. These are the ones that are considered blow-off hatches. Basically just a big chunk of metal over an open hole. Usually they'll put a tether on it so that if it does blow off, you know it's not going to end up in the break room. But the one nice thing about ENARDO's vertical lift design that you can see there, I believe that's the model 2100, is it has guides to assist in reseating. And those guides can also be removed so that if you need to open that up to get access to the tank, you can still get that. The hinge design, though, is really what we prefer to see. It's designed so that you get constant reseating, and then we can also have emergency vacuum capability on these as well. So it's important to consider how the conservation vent and the emergency vent work together. And obviously we need to take that into account. Like Rhonda said, we use API 2000 as the standard for sizing all of our vents. API 2000 main body for the normal vents, and then the emergency vents, if it's a volatile liquid, we'll use the Annex A. But more importantly, what we have to look at is the buildup required for these to hit capacity. So this is an example of a flow curve that was test data ran by an independent laboratory, and we have these for all of our products. But so if you look here, we've got flow rate along the bottom axis there, and then pressure in inches of water column along the vertical axis, and then you can see the curves for a 2-inch up to a 12-inch conservation vent. So if we're looking at a 4-inch conservation vent set at 1-inch water column, basically what we're going to do is see, okay, if we need 35,000 cubic feet of air per hour, we can see that we can achieve that at 3 inches water column of pressure. And basically what that translates to is that's the 2-inch water column buildup or 2-inch water column of overpressure that we need above the set point to make sure we can hit capacity. So then we have to look at that in respect to the emergency relief vent. And we consider that green range there our normal breathing range. And the normal breathing range is where we want to be for our basic operation. So essentially, we want to design these tanks and all the equipment on them so that the emergency relief vent never has to lift. So if we can stay in that normal breathing range with our conservation vents and make sure that we hit our max out breathing at a decent point, we'd like to keep that at roughly 75% of the emergency relief valve set point. And once again, that's just to make sure that that emergency relief valve doesn't have to lift or open up for vacuum unless it's absolutely necessary to. So there's a lot that we kind of just threw at you guys about what we do when we're sizing and considering set points to protect your tank. This is just an example of all the information we're going to ask you for when you request a quote or we're looking at replacing a tank vent in your facility. So we're not going to run through all of these. The one that we need to take into consideration is if it's an existing tank, obviously you guys have connection sizes that you need to keep in mind. We don't want to have to modify tanks every single time we swap out a valve. And if needed, this is where we can move to our full lift or our pilot operated designs. If we need extra capacity out of the same connection size, we can utilize those other technologies to achieve that without having to modify the tank. So here's some installation examples of what we typically see in the field. On the left here, this is a pretty common, just an ENARDO 950 conservation vent there, breathing to atmosphere. We've got a Series 2000 emergency relief hatch, and then finally an ES 660 thief hatch that can be used for checking the tank if you need gauging or to check level, anything like that. On the right side is more of a standard setup for what we would expect to see within fermentation of an ethanol plant. You've got a CO2 scrubber constantly pulling a vacuum, and then an ENARDO 850 series pipe away model. The pipe away and the vent to atmosphere is just the difference between the 950 and the 850. They operate pretty much the exact same. It's just the 850, then those vapors can be sent to the scrubber as well. And then we've still got a Series 2000 emergency vent. One thing to keep in mind is that both of these tank tops only have one layer of vacuum protection. We would need to move to a Series 2500 emergency vent to have emergency vacuum protection as well. And while it may seem, you never need them, we've seen, simple things like somebody was on top of a tank painting it, and they put a trash can or a trash bag over the over the conservation vent. They left it up there, put the tank back into service, and all of a sudden it sucked the tank in because it wasn't able to in-breathe through the conservation vent. So simple things like that are why it's always a good reason to have a second layer of protection. Here's another example. If we get into a scenario where we need an additional connection and we can't make modifications to the tank, it is possible just to do some custom piping setups like that, and we can get those with the products mounted on them as well, so that way you can get more devices if you're limited by connections. This is one scenario that we often run into when we're looking at volatile liquids or finished product storage tanks. If you need to vent the product off but have risk of ignition on the top of your tank, if, for example, there's an agitator or some other type of motor on there that could spark, what we do is we use a pipe away unit, and then we actually just vent it further away from the tank. It's not necessarily going back to a scrubber, but we still need to use that pipe away unit to make sure the vapors get away from that possible ignition source. And then here's another example. You can see there's two conservation vents there that are on one connection, and we've got a large piece of Y pipe there. This one, we were actually limited on size. So our conservation vents go up to 12 inches, and for this application, we needed more vacuum capacity. So you can see the conservation vent on the left is both pressure and vacuum, while the one on the right is just vacuum because we needed some additional capacity there. And while we're running through all of our sizing and selection, all those questions we're going to ask you guys, it's everything that we're putting into what's called ENARDO Soft Calc 2. And if anybody in your plant is a do-it-yourselfer, this is available for download online. It's a free software we offer. Very simple to use. Basically, it's going to ask you which product family you're in. It'll ask you to select the product that you want to take a look at. And then it's going to give you a list of all the required inputs. And you can see there you can choose between API 2007th edition and then Annex A. You can switch between the different product families, and this will calculate the required outbreathing and inbreathing that you need, as well as recommend which size of product you need to be in and tell you how much overpressure you need to hit that capacity. What's really nice is then you can even choose the materials of construction you'd prefer, and it'll kick out a model number that you can send to us. So now we're just going to go ahead and roll straight into tank blanketing and vapor recovery regulators. So on the layers of tank pressure control, this is the base layer. And while this isn't common to see in fermentation, we do see this a lot of times on your volatile liquids or your finished product storage tanks. If you're not using a floating roof design, we'll see tank blanketing and vapor recovery. So starting with blanketing, this is also known as padding the tank. Basically, all we're doing here is taking an inert gas, typically it's going to be nitrogen, and putting a blanket of that on top of the liquid, so we avoid outside air, mainly oxygen, from being breathed into the tank. That way, we're not allowing oxygen to mix with the combustible vapors and possibly ignite inside that tank. It's also going to protect if there's any possibility of the liquid spoiling if it comes into contact with anything in the atmosphere. These tank blanketing regulators, you can see one there on the left. That's a Fisher ACE 95. They operate like any standard regulator, but you're going to notice that they have very large diaphragms. That's because they're extremely accurate and they have to operate at really low pressures. On the gauge there, you can see this one's controlling down to a 1/2-inch water column. So like I said, they operate like any other regulator that you see within your plant, whether it's on a methane line or your natural gas line. All regulators have the three essential elements. So we have our restricting element, which is a plug and orifice or a plug and seat. We have the measuring element, the diaphragm, and a loading element, which we use a spring so that you can wind in your set point. And so the regulator is going to be sensing downstream pressure. In this case, it's the pressure inside the tank. That pressure registers on the diaphragm and will move that diaphragm up and down, which is connected to the plug, and that'll move accordingly as well. So if pressure in the tank drops, the diaphragm moves down, the plug moves away from the orifice, and we get nitrogen breathing into that tank to make sure we're keeping it at the proper pressure. On the opposite side of that, so that was for inbreathing, when liquid is being pumped out of the tank, we have vapor recovery, which would be similar to like a CO2 scrubber on the outbreathing side. And so once again, it's basically just a back pressure or a relief regulator. which the only difference there is we're sensing pressure on the inlet side. So once again, we're sensing pressure in the tank, but as pressure in the tank builds over a certain point, the diaphragm will move up and compress that spring, lifting the plug away from the orifice and allowing those vapors to get out of the tank. So vapor recovery, also known as PAD. Once again, we have tank blanketing or PAD. Vapor recovery is DPAD. Is essentially making sure that these vapors don't just breathe out to the atmosphere. If they're not going to the atmosphere, typically we'll see them go to a scrubber, sometimes a vapor recovery unit, or not. It's pretty common to see them just go to a flare as well. One thing to note is that a vapor recovery regulator is typically going to be much larger than a tank blanketing regulator, just because it has a very low pressure drop across it. So while you may have a 1-inch tank blanketing regulator, you could have a 2-inch or even up to a 4-inch vapor recovery regulator.
Thanks, Isaac. Our next speaker is Sean Collins-Dipple. He's the Process Level Product Manager for Emerson. Go ahead when you're ready, Sean.
All right, so we've learned about why it's important to protect your tanks from overpressuring. Now we'll talk a little bit about why we need to measure level of the tank to prevent anything from overflowing out into your plant or into your containment areas, and how to do that best. So there are a number of different level technologies on the market. I'm sure some of you have seen or have tanks in your site where you've tried more than one, maybe even half of these different types to get the correct level measurement or the best measurement for your plant. And that's just because there's no one single technology that is going to work best for measuring level across any industrial plant. So here at Rosemount, we have a number of different level measurement offerings. We'll talk about a few of them today. I'm not going to be able to go in super in-depth on all of them, but we will touch briefly on differential pressure, guided wave and non-contacting radar, point level detection, briefly on solid level measurement, and then on automatic tank gauging as well. So I'm going to start with differential pressure, mostly because it's the most common one still used on the marketplace. It's very reliable and well understood. There's no moving parts. And because it's based on pressure measurement, it doesn't care about anything going on in the vapor space of the tank or any foam or agitation that might be occurring either. It also doesn't care about any sort of internals going on in the tank, whether it's baffles or mixer blades or heating or cooling coils. And by using diaphragm seals, you can extend the use of your differential pressure measurement to extreme temperatures with different fill fluid, or corrosive or dirty processes with different coatings or metals on the diaphragm seal. So you may be thinking, great, differential pressure sounds awesome. Why don't I just use that everywhere? Well, one of the things you have to be concerned about is that because it's a differential measurement, it often requires 2 taps. And if you're going to be using capillaries, those can get very long and difficult or expensive to install. If you've got like a fermentation tank where your density of your product is changing, that will cause the pressure that the transmitter sees to vary as well, which will give you varying level measurements back in the control system. Another thing to be concerned about is any variation in ambient or process temperature will have an effect in that capillary fill fluid and shift the pressure seen by the diaphragm on the sensors as well. It is only good for liquid, so if you're trying to measure a solid material like, say, corn or ground powder, the differential pressure is not going to measure that. And if you've got recessed nozzles that have the capability of plugging or coating with a suspended solid, that can mess up the reading as well. Next technology we'll talk about, and we'll group them together because they're based on a similar principle, is guided wave and non-contacting radar. They're both very good for for industrial level measurement. They're based on a dielectric principle, so changing densities of your process media won't have an effect on the reading. And they are able to withstand turbulence or vapors in the vapor space, any dust in the vapor space, and any sort of geometrically difficult vessel. So it doesn't have to be a perfectly round or cylindrical vessel for a guided wave or non-contacting radar to work. Because there are no moving parts, they're easily able to install in the chamber and replace a mechanical device that might be causing maintenance issues or sticking. Guided wave is also very good for interface level measurements because it's guided down the probe. It'll be able to see the top level measurement and then pass through that low dielectric top media and see the interface between that and your bottom liquid media for like a corn oil separation tank where you've got corn oil on top and the water on the bottom. We're also able to use guided wave radar for saturated steam applications. Normally, the dielectric of air is 0, but if you're boiling off steam or hydrocarbon, that changes the dielectric of your vapor space, slows down the signal, and with our DVC radars, we're able to compensate for that and still give an accurate reading in saturated steam or boiler applications. We're also able to use guided wave and non-contacting radar for solids measurement. For skinny, tall silos, corn is a great application for guided wave radar. We can also use non-contacting radar in large storage tanks, reactor and mixing tanks. There is no concern with a non-contacting radar for it to hit any sort of impeller blades that might tangle up the guided wave radar probe and even pull that off. We're also able to mount non-contacting radars on top of pipes or stilling wells to give a more even surface inside a potentially turbulent vessel. Some of the advantages of radar over other level measurement technologies is it's a top-down measurement, so it's easier typically to have a nozzle added to the top of a vessel instead of trying to cut into the side or the bottom of the vessel. Again, it's not based on density measurements, so any sort of density changes inside the vessel won't affect the reading. And it's virtually unaffected by dust, vapor, or anything going on in that vapor space that might affect, say, an ultrasonic measurement. There are no moving parts, so there's nothing to worry about getting stuck or causing maintenance headaches. And you're able to use it across liquids and solids measurements. It's not tied to a single process media. Guided wave itself specifically, because it's based on a probe, you don't have to worry about an antenna or a parabolic antenna going into the vessel, can handle smaller process connections. And you're also able to do interface measurement with a guided wave radar that you can't do with non-contacting radar or is difficult to do with DP level. But like any level measurement technology, there are a few other considerations or drawbacks to doing a radar technology. For guided wave, because it's contacting, if you've got a corrosive or dirty fluid, you need to make sure that the probe either has the right metallurgy or coating on it to prevent that probe from getting eaten away or broken. If there's any sort of agitation in the vessel, mounting the probe in the correct location so it doesn't get tangled up, or that it's secured at the bottom and doesn't get swung around and hitting the side of the vessel is a big thing to be concerned about. One of the other concerns is long, narrow nozzles. Those can actually absorb a lot of the radar signal and not send enough of it down into the vessel to give a strong enough return signal from the level in the vessel to get an accurate reading. With non-contacting, like I mentioned, it's a surface reading only, so you can't do level and interface with that. And foam in general is unpredictable. You can have a light dishwasher type foam that is easy to penetrate with a radar signal, or you can have something very thick, dense, and viscous that might actually simulate an actual level reading and not give you the true level of your liquid in the vessel. So as far as mounting these to kind of try and avoid some of those concerns, avoiding long nozzles or any sort of reduction nozzle where you can eat away a lot of the radar signal or cause false readings is a big concern. Our rule of thumb for nozzle height is to have it be less than the nozzle diameter plus 4 inches. That way you maximize the amount of signal sent down into the vessel. You want to make sure not to have the probe or even the non-contacting radar right above the fill stream, as that will interfere with the level measurement and make it seem like your inlet pipe is where your level is, even if it's not actually the case. And any sort of contact between a probe and a metallic object will spoof out the signal and make it seem like the level is where the probe is contacting the metal surface and not where the actual liquid level is at. We'll move on from radar into point level detection. Here at Rosemount, we have vibrating forks as our point level detection, so we'll talk about that. There are a number of different offerings in our portfolio, from the compact 2110 model to the more standard, most commonly seen 2120. We also have a wireless 2160 model for remote regions where it's either difficult or exceedingly excessive to run conduit and wire out to a device. And we just recently came out with the fully wired HART version to give you advanced diagnostics back in the control room to prove that the fork is working without having to go out into the field to verify that it's still operating correctly. Where should we use forks? Ideally, we would put them everywhere we would want a continuous level measurement as a backup reading, especially as a high level or overfill prevention. That way, if the continuous measurement locks up into a false reading or breaks for some reason, you still have a high level protection to make sure you don't overfill and flood your vessel or cause it to collapse. We also recommend using vibrating forks or point level for pump control and run dry protection. That way you don't accidentally cavitate your pump by thinking there's liquid running to it when there really isn't. Some other applications or concerns as far as installation. Similar to a continuous level device, you don't want to install a vibrating fork right under a fill stream or right next to an impeller blade, as those can either give false trips or potentially break the vibrating fork. If you've got a vessel where there's suspended solids that could settle out, if there's a recessed nozzle or buildup on the sidewall, we want to make sure that those forks are extended far enough into the tank that they don't get any sort of bridging to cause false trips. And because we can do extensions up to 12 feet long on those forks, we want to make sure that every 1 meter or just over 3 feet we add support to avoid having that neck break off and then give you a false sense of security that the fork is still active when it might have broken away. I'll touch briefly on our solids portfolio since there are still solids measurement applications in your facilities. And we have 3 different continuous devices for measuring solids. I've talked already about guided wave radar and non-contacting radar for liquid level measurements. They can also be used for the low dielectric solids measurements in small process vessels. Typically narrow silos work best for this. And for your larger inventory control offerings, we have a acoustic 3D solid scanner that is able to fully map out the surface of a solids silo or large inventory vessel to give a better inventory management than a single point level device. The last thing I want to talk about for level measurement here is an automatic tank gauging system. Now, for a standard process vessel, having an automatic tank gauging system or even a manual tank gauging system might not be necessary, but for large storage vessels or places where you're doing custody transfer, having a full automatic tank gauging system to have an accurate measurement in your large final product storage vessels is a good idea. Even if you have, say, a density flow meter to use for your custody transfer, if that ever needs to get pulled out of service or stops working, being able to have a backup reading with an automatic tank gauging system is a great idea. It gives you a full volume measurement, and it's based on a system of several instruments around the vessel, not just a single level device. So with it being a full system, you get a level measurement device. You do measure the temperature of the vessel. This can either be a single spot measurement, or we offer a multi-spot device with a single penetration, as well as vessel pressure. And from this, you're able to derive the gross volume inside the tank, as well as the density and mass of whatever liquid is inside your vessel. By having it be automatic tank gauging instead of relying on an operator or technician to walk out to the storage vessel, climb up on top of it and try to do a hand dip, or relying on a mechanical device such as a float and tape, you're able to have improved safety because you're no longer climbing up on top of a vessel, opening a hatch and potentially being exposed to hazardous or noxious fumes. You have a better inventory control as you have a more accurate reading instead of relying on potentially inaccurate hand gauging or floats and tapes that may get hung up as they're trying to move up and down with the floating roof. And because you have a more accurate measurement, you're able to increase your utilization of the tank volume. And like I mentioned again, it's able to be a good backup for any sort of custody transfer flow meter that you may have if that ever needed to get pulled out for service.
Excellent. Thank you, Sean. So we'll hand things back for the rest of the presentation. Will be handled by Isaac Dressler. So Isaac, go ahead when you're ready.
All right, I think I've got control back here. So we're going to dive into flame arrestors. And so why is learning about flame arrestors important? Well, obviously pretty much any biorefining or ethanol plant is going to have one on their flare somewhere in their loadout system. But really, it's important to consider flame arrestors because if they are not properly applied or properly maintained, their results can be catastrophic. So these photos here, this was some type of petroleum loadout terminal. I think it was down in Texas or Oklahoma, and they had the wrong flame arrestor applied and managed to pop the lid off of every single tank in their facility. I was told the story that there was actually someone in that camper when these all went, and luckily he was unharmed. Yes, we don't know about the same for his pants. He probably had to go out and buy some new ones. So how flame arrestors work is essentially we just remove heat from the combustion pyramid. This is essentially because a flame arrestor is really just a big heat sink. Here on the left, you can see a schematic of how a flame arrestor works. So the vapors flow from left to right, and the right we would consider our unprotected side, or typically that's where your flare is going to be. And it's important to remember that a flame arrestor does not extinguish the flame. Though that cell in there, which is really just crimped metal wound and around, doesn't allow the flame front to pass. So it stops the flame right there and keeps the vapors on the other side below their ignition temperature. This way you stop the flame at a single point in the line and it doesn't spread throughout the rest of the system. A flame arrestor is considered a passive safety device because it doesn't require any outside power or influence in order to operate. An active safety device, which can accomplish the same thing, something like a liquid seal, you have to make sure that you've got enough liquid in there so that it actually does its job. So flame arrestors can just give you a little more peace of mind because you know that they're going to be able to work. Oh, sorry, I jumped one too far ahead. So as we talk about flame arrestors, there's two main terms that sound similar but mean very different things. We have deflagration and detonation. Deflagration is a flame front traveling through the pipe at subsonic velocity, and detonation is a flame front traveling through the pipe at supersonic velocity, and it's typically characterized by a shock wave. How we move from deflagration into detonation is typically a factor of what we would consider run-up pipe on the unprotected side. So it's the piping that's in between your flame arrestor and the source of the ignition. And there you can see an excerpt from an ISO code. But essentially what it's telling us is the more run-up pipe that you have and the more elbows or anything that changes the cross-section of the pipe, it increases not only the velocity but also the pressure of that flame front. And essentially, as we see that flame front traveling through the pipe, these are the different stages that it goes through. So near the source of the ignition, it starts as low pressure deflagration. It picks up speed traveling down the pipe, moves into high pressure deflagration, and then eventually as it goes through an elbow or just has more run-up pipe, it's going to go into detonation. And it's important to note that before we can get to what we consider a stable detonation, it has to go through overdriven or unstable detonation. And that's the single point on that curve that has the highest pressure and the highest velocity. So that's what we need to make sure we're protecting for. When we look at ENARDO's flame arrestor portfolio, there's three basic types. We have an end-of-line arrestor. So this is just if you need to vent any vapors that are combustible to the atmosphere. This is installed at the end of the pipe, so we don't have to consider any run-up pipe where a flame front can pick up speed. So these are very simple arrestors. Then we have an inline deflagration arrestor, and the installations for those, we are limited by run-up distance, obstructions, all those things that cause the velocity and the pressure to increase. And then finally, we have a detonation arrestor. And all ENARDO detonation arrestors are unstable. Remember, an unstable detonation is the highest velocity, highest pressure point on that curve. And that's why ENARDO only makes unstable detonation arrestors, so they can be located anywhere in the piping system. There are other manufacturers out there who produce stable detonation flame arrestors, so you need to be sure that if you have a stable detonation flame arrestor, that you're following the installation limits as well. This is a chart that's in our product catalogs on the ENARDO flame arrestors so that you can see basically what the requirements are. So as we move left to right across the columns here, we have the end-of-line flame arrestor, the Series 7, which is our low-pressure flame arrestor, Series 8 is our high-pressure deflagration arrestor, and then finally our detonation arrestor. And as we move down the rows, what we're looking at is the maximum length of run-up pipe that you can have with no bends, maximum length of run-up pipe you can have with up to one bend, and then the maximum length of pipe with multiple bends. And then that final row there before the operating pressure is basically saying how long a flame front can sit on that arrestor before it'll pass through. And so you can see for the end-of-line flame arrestors, once again, there's no run-up piping to consider, but it can hold a flame front for 5 minutes before it'll pass. The ENARDO Series 7, which is our low-pressure deflagration flame arrestor, can have up to 20 feet of run-up piping, so that's 20 feet between the ignition source, which is commonly the flare or some type of a blower motor, to the flame arrestor. You can have 20 feet of pipe with up to one bend, and it'll hold a flame front for 5 minutes. The high-pressure deflagration, ENARDO Series 8 flame arrestors can have 60 feet of run-up pipe, and then finally the detonation arrestor you can install anywhere in your piping system. It can hold a flame front for up to 2 hours before it'll pass through. And so that just kind of gives you more peace of mind and knows that regardless of wherever you install it, it's going to be able to stop that flame. One thing to keep in mind, though, is as we move left to right here again, the cost is going to increase. So the main difference between a deflagration flame arrestor and a detonation flame arrestor is honestly just the amount of metal that's inside. So the two images on the left are a deflagration flame arrestor and then what we would consider the the cell element from inside that. And then the two images on the right are a detonation flame arrestor and then also the cell or the element from inside that detonation flame arrestor. You can see for the detonation flame arrestor, there's just a lot more of the cell. It's a lot longer. That's why it can last up to 2 hours before that entire cell heats up and allows the flame to pass. Also, it's much more rigid with how it's constructed. That's why it can take those higher velocities and higher pressures. Also, when we're looking at flame arrestors, we have to consider the gas group of the vapor that's going through the line. So there are NEC and IEC gas groups. Typically, we use the NEC gas group, which is B, C, or D. And these are determined by the maximum experimental safety gap. And basically, that's a test that's done by a standard body so that they can figure out what is the largest gap where these vapors can flow through, but they won't allow a flame front to pass through. And so all of those tests are ran, and that's how we decide what size of crimp we need to have in that metal element or flame cell in there. So you can see based on what's flowing through your pipe will either be in gas group D, C, or B, and that's just the level of protection that's required for those vapors. Here's some examples of arrestor applications. On the left there, we have some end-of-line vents with flame arrestors on the end. In the middle, we have a conservation vent with an arrestor on it. That's actually a competitor's unit just to show you that that is a standard industry practice. That's not just something that we do. And then on the right, we have a loading rack, which is really common to see flame arrestors all around a loading rack. Most common installations for anybody in biofuels or ethanol is going to be the flare system. On the left there, you can see a couple of flame arrestors actually on that flare system. It's also common to see them if we do have vapor recovery. This is a marine vapor recovery skid shown on the right. So one of the most important things to consider with flame arrestors, while they are passive devices, you do need to monitor and inspect them. We recommend inspecting them annually just so that you can do a visual inspection to determine if there's any corrosion issues or any wear issues like that. But for monitoring, the most important is to monitor pressure drop. By monitoring pressure drop, we can tell if that flame cell is becoming plugged at all. So when you initially install that flame arrestor, you should measure what the pressure drop is against it or across it. We size those so that they're minimized, and then over time, you'll slowly see that build up. And as they build up, you need to make sure to clean those elements, because any debris in there also gives you a potential risk for a flame front to pass. It's also very critical that you monitor temperature on the unprotected side of a flame arrestor. So this would be the side where your flare or potential ignition source is. You can see on the top picture there, the flare would be off to the left. That was a flame arrestor that had an aluminum housing, and the flame front sat there for a long enough time that it actually melted that housing. The picture on the bottom is more commonly what we see installed at facilities in our area. It's carbon steel housing, but you can see the flare would have been on the right side, so the unprotected side there didn't have a temperature probe installed, so they didn't realize how long a flame front was sitting on that arrestor, and it stripped all the paint off halfway through that flame cell. So using a temperature probe, you can then have it feed back into an alarm system and alert your control room or a PLC to actually have an alarm on it. You can also utilize an isolation valve or a slam shut valve to shut down the system, or you could purge the system with nitrogen, CO2, steam, or anything that'll snuff out that flame. When you're doing your visual inspections once a year or more frequently than that, damage that you're going to look for is pretty much any interruption within those flame cells. So this is looking at where a flame cell meets up to the housing, and you can see where they aren't nice straight lines anymore. They've been kind of pulled away, and that damage indicates that a flame front has hit that flame arrestor before, and that this should not be put back into service. They don't always happen on the edge. They can happen right in the middle of the flame cells. It just depends how that flame front hits it. So it's important that you give the entire thing a good look over. When it comes to maintenance, cleaning the flame element or the internal piece there is the most important step. You can use solvents, water, steam, just about anything, and flow it in the opposite direction of normal flow so you can get any debris to wash out of there. You can clean them just about any method other than trying to stick anything into the flame cell. So don't think you're going to take a piece of wire or a wire brush and clean it out. You need to just typically run water or some type of cleaner or steam the opposite way so that you don't damage those elements. Those elements are just stainless steel, so they can handle most chemical solvents, but you need to make sure there's nothing sharp that you're trying to shove down in there. Then you need to replace the gaskets where the element seals tight to the housing, and tighten the bolts to the specifications shown in the manual. We always make sure to do a pressure test on them so that you're not leaking anything to atmosphere. It's also recommended you can have just a spare element and swap those out. So basically you leave the flanges installed in the pipe. And this way, if you want, you could swap the elements out and send it back to us. We can clean it, give it a once over, and ensure that it's up to code and still good to put back into service. So you can keep a spare element or just an entire spare unit. That way we can pressure test it for you and reassemble it with new gaskets. So we threw a lot at you guys today, but everything that we talked about plays a critical role in ensuring your tanks are protected. I'm not expecting anyone coming away from this call to be an expert on this stuff, but we wanted to give you an intro into your tanks and the equipment that keep them safe. If you want to ensure total tank protection, we do have two paths forward. If you want someone on your team to have in-depth training on these devices and know how they operate together, basically somebody that'll own this equipment within your plant, we are hosting a tank university on March 26th near Sioux City, Iowa. It's actually going to be up in Dakota Dunes. This is a one-day training. It's very similar agenda to everything we covered today, but we're going to dive in deeper on each of the topics. And we'll also have demos available for anybody who likes to get hands-on. I know I personally learn a lot better about actual equipment when I can get hands-on with it. Another option, if you prefer us to come to you, we do offer tank surveys. For these, we get a couple of experts to come to your site and review installations of all your tank protection equipment. We'll walk around, photograph each device, take notes about its condition and installation. We'll get all the process conditions from your plant engineers, and then we'll provide you a detailed report of recommendations based on what we see. So with that, Lisa, I think we're going to open it up to questions.
Yes, we are. Thank you, Isaac, and thank you to all of our speakers. We do have a few questions coming in. If anyone has more questions, please keep typing them into the designated question space on your screen. We have a little bit of time to do that, so I'll start at the top here. The first one, in your discussion of PVRV, you list inbreathing of oxygen. Do you really mean inbreathing of air? Since pure oxygen is available, but it is quite dangerous.
Yeah, I did mean to say just breathing in of atmosphere or the air around the tank. Typically, we're mostly concerned about oxygen getting into those tanks because when it mixes with the vapors, it creates the potential for an ignition inside that tank. So yeah, I should have specified and said atmosphere or air.
Great, thanks, Isaac. Next question, can you replace a flame arrestor when the unit is in operation?
No, you will need to take it out of line. You can leave the flanges on each side in line, and the flame arrestor can essentially just swing out, but you will have to shut down that vapor recovery or your flare system in order to do that.
All right. What do you do when PVRV capacity calculated is exceeding your charts?
If it's exceeding the chart, basically we have two options. We either move to a larger size or we can go with multiple devices. Obviously, we're limited by connections on the top of the tank. So that's when we would look at either the full lift or the pilot operated designs. We can get more capacity out of those designs with the same connection size. Obviously, there's increased risk with that or increased cost with that. So it's something that we have to consider. We're going to try and get you the lowest cost option, but we want to make sure you're protected.
Excellent, thank you. How are the PVRV taps placed on the top of the tank? Are they close to the sensor?
It really doesn't matter. You don't want them right next to the edge, but it's essentially just wherever the flanges on top of your tank are. I think those are spec'd out in the API 620 standard for design and construction of those tanks, though.
And how do you establish settings of multiple PVRV?
So as long as they're all conservation vents, you can have them set at the same set point. We only need to stagger set points between the different layers of the protection. So we want to make sure we have room between the tank blanketing regulator and the conservation vent, and then the conservation vent and the emergency vent. And then enough room for the emergency vent to hit full capacity before we hit the maximum allowable working pressure or working vacuum of the tank.
All right, one more here. What is the spark gap gas group for ethanol and or different grades of ethanol? I have found some confusion in the past as it appears to sit on the boundary between grades and be confused with E10 or E85.
For the NEC gas group, I believe they fall into category D, but I'm going to have to dive into that one for certain. So whoever had that question, feel free to reach out to Paul Wagner there, and we'll get in contact and I'll clarify that.
Great, thank you. Do you measure a plugged flame arrestor by delta pressure?
Correct. So you'll want to measure pressure on each side of the flame element. Typically, we'll sell the ENARDO arrestors with ports on the inlet and outlet side specifically so that you can do that. And so you just want to make sure you measure that either once a month or every couple of months so that you can see that build over time. And once it hits a few inches of water column, you'll want to make sure you get that element pulled out of line so you can clean it.
All right, excellent. Thank you. A lot of great questions coming in. We still have some time, so if you still have some questions, some follow-up inquiries, please keep typing those in. Still have some questions to go through here. Do we have to be shut down for you to complete a tank survey?
No, you do not, actually. We'd prefer that you were operating so that we can see how all the devices are normally working. So as long as you keep everything live, we'll go ahead and run around. If we need to get hot work permits, anything like that, we typically have to go through those safety precautions. But we prefer that the tanks are live and that the process is live.
All right. How often should I service my tank vents?
I would start annually. If every year you're checking them and they look to be in good condition, then you could maybe back off. Or if you're finding a lot of debris or damage in them, then you should increase that interval. But start with annually is a good starting point.
Do all these principles apply to double wall tanks as well?
That would be called out in API 620. So all these principles are for low pressure storage tanks. I guess I don't know off the top of my head if a double wall tank is low pressure, meaning 15 PSI or below. We'd have to double check on that one. So for that one, once again, feel free to get a hold of Paul Wagner and we'll double check that question for you.
All right. We'll put Paul's information back up on the screen. There it is. Next question. What are the most common issues with conservation vents?
Typically, it's going to be the freezing. That's the one we see most commonly in this area, just because, and when I say this area, I'm talking Iowa, Minnesota, South Dakota, Nebraska, and Illinois. These areas, obviously, we can get hit with things like a polar vortex or just a 3-day blizzard where any moisture can get in there and freeze the pallet to the seat. It's also really common to see debris build up over time. So any freezing or sticking, typically that's why we like to go with ENARDO in this area, just because that PPS is our standard material. So there's no additional cost or lead time for it. And we know that we're good to negative 50 degrees and virtually nothing sticks to it.
And I have another double wall tank question, Isaac, so I don't know if we'll be able to answer that, but Paul's information is still up on the screen if we can't. But the question is, for double wall tanks, the PV-RV connections should tap on inner tank or the outer tank?
It's going to have to be the inner tank, I believe, but once again, we'll want to clarify that one.
Okay, great. So Paul's information is still up on the screen for that follow-up question. We have a couple more here that we'll have time to go through. Can vents be serviced on-site, or do they have to be sent in?
So if you're working on a conservation vent on-site, if it's a design that has a cast-in seat, basically you have to come in with a lapping block. It's doable. It's just not very fun to do in the field, and that's how you can machine that seat down to make sure it's a like-new finish. The ENARDO design, since they have that removable PPS seat, if those become damaged for any reason, you can come in, remove those on site. It's a really simple rebuild, actually, and then replace the rest of the soft goods in there as well.
Okay, excellent. So we have one more question. Last question is, do we have to have wireless position transmitters?
No, we do not. We have wired or wireless position transmitters available for any of the ENARDO conservation vents or the emergency vents as well.
One more just came in. We do have time for this question as well. So one more. What is the life duration of these devices?
Unfortunately, the answer for that is it depends on the service. It's not uncommon to see some of these ENARDOs that are installed, 20, 25 years old with basic maintenance and, regular inspections. All the critical pieces can be replaced. So as long as you're not getting any pitting or extra wear and tear on the actual body, we can replace everything inside of an ENARDO, and the life expectancy is probably longer than you're going to be working at your plant.
Okay. I do have one more, so since we still have time, we'll just keep reading these. Any attendees that have more questions, please continue typing those into the chat function on your screen. Next question is, any recommendations regarding the standard distances for high-level protection and clearances of the tank levels and or with reference to other items such as in-tank foam protection or other top entry nozzles?
That's going to be a question for Sean, Lisa.
Yeah, so that one is it depends on the service. What I have used in the past is that your high level, most tanks that I've run across, if they have some sort of overfill prevention or vent line, we would want the high level to be at about 90% of the usable volume, where that 100% line is where that overfill happens. As far as a little bit more in depth, that's something we could cover either at Tank University or reach out to Paul and he can work with me as well.
Excellent. Thanks, Sean. Paul's information is still up on the screen. So anyone who wanted to reach out to Paul with those follow-up questions, anything that wasn't able to be answered during the Q&A today, please feel free to do that. A special thank you once again to our sponsor, Stover Controls, an Emerson Impact partner. We have a special rate for webinar attendees for the upcoming FEW in Indianapolis. Call the number on your screen for $50 off the early bird rate. And when you do that, be sure to mention FEW webinar. We also have a few upcoming events to be aware of. A Biomass Magazine webinar March 12th, Explosion Risks and Mitigation Methods for Critical Process Equipment in the Biomass Facility. The International Biomass Conference and Expo is coming up March 18th through 20th in Savannah, Georgia. And of course, the FEW June 10th through 12th in Indianapolis with its traditional Ethanol 101 pre-conference on June 10th. A big thank you again to our speakers, our sponsor, Stover Controls, and all attendees who tuned in today. Enjoy the rest of your day.